This is lecture 3 of kinetics. In this lecture, we're going to link kinetics to reaction mechanisms. I'm going to introduce the concepts of elementary reactions, the rate limiting step, and reaction molecularity to you. So the lecture objective is to be able to explain how information about reaction rate links to the mechanism of a reaction. When we're doing this, we have knowledge of the overall balanced equation of our reaction, and we know that this will represent a sum of a series of elementary reactions, so a series of steps that take place in order for the reaction to occur. We can use the rate law to suggest plausible reaction mechanisms because we know that the rate law will link to the stoichiometry of the rate determining step. So the elementary reaction that is the slowest. So the slowest reaction will be the reaction within the mechanism that determines the rate. And we also know that the sum of the elementary reactions that take place for a reaction to occur must equal the overall balanced equation. But why do we want to do this? So we want to do this to understand fundamental chemistry. And these concepts will help us also in the next lecture, allowing us to predict a drug product life. Not all parts of a reaction influence the overall reaction rate. That is what we can tell from the fact that it's only the rate determining step, the slowest step in the reaction, that will determine the rate of the reaction. Best way to understand this is to use an example. So here we have an example that we've seen before. So we have hydrogen peroxide that can decompose to form water, 2 molecules of water and an oxygen molecule. So this reaction, if you look at it, and if it was a reaction that was a single step, so if this reaction took place as a single step, then you would look at it and think it must be a second order reaction with respect to the hydrogen peroxide, if it's an elementary step, if it's a single step reaction. But from experiment, it's found to be only first order with respect to the hydrogen peroxide. So that tells us the reaction mechanism has multiple steps in it. Reaction can be carried out in alkali media with iodide ions as catalysts. And the rate law was found experimentally to be that the rate of the reaction, so the rate of decomposition of the hydrogen peroxide, equals K, so the rate constant, times hydrogen peroxide times the concentration of the iodide ions, both to the power of 1. So both first order with respect to both of those species. So what does this tell us about the mechanism of this reaction? What we need to do is to come up with a plausible mechanism. And that plausible mechanism must hold true in 2 things. It must have that one of the steps only uses 1 molecule of hydrogen peroxide and 1 molecule of iodide ions, to mean that there is 1 step that can be called the rate determining step and that would match to the rate law. And if you add both of the steps together, you must end up with a reaction that the overall balanced equation matches the reaction that we know. So those 2 things must apply when we come up with our plausible mechanism. And this plausible mechanism here gives us these 2 things. So step 1, you can see are based to the rate law. So it's one molecule of hydrogen peroxide and one molecule of the iodide ions. And that forms one of the molecules of water plus an IO minus ion. And then the IO minus ion reacts with another molecule of hydrogen peroxide in the second step to form to form water plus the oxygen plus giving us the iodide ion back, because of course the iodide ion is a catalyst here, so that means it won't be used up in the reaction. And if we then look at the overall reaction, so in other words, add up the components from both sides of these two reactions, and then take away anything that's on both sides, we will end up with a reaction that is two hydrogen peroxide molecules going to form two water molecules and one oxygen molecule, which of course is the overall balanced equation for this reaction. So we have here a mechanism that fits to these two known things. It fits to the overall balanced equation, and it fits to the rate law that we have for this reaction. Okay, so this tells us that step one of this reaction is the rate determining step, and that's the step that defines the rate law. And of course, that the sum of the elementary reactions equals the overall balanced equation. You'll notice that we have here an IO minus molecule, and that is our intermediate. And the molecularity of both of these elementary reactions is bimolecular, which means that two molecules react with each other in both of those steps in that reaction. So that reaction has two steps to it, and the first step determines the rate of the reaction. Let's have a look at this reaction here. In this reaction, there are three steps that have been proposed in the mechanism, and this mechanism is listed here. So you can see step 1, step 2, and step 3. And step 1 is believed to be the slow step, so that's the step that must link to the rate law. So from that mechanism, what do you think that the rate law is? Now, I trust when you've looked at this, you have said, right, the rate law will link to the slow step of the reaction mechanism. So the rate law will relate to the reactants of the slow step, which means that the rate will equal minus K and then multiplied by the concentration of C4H9Br. Okay, and that is the rate determining step, which is the slow step of the reaction. What is the overall balanced equation? So to get to the overall balanced equation, you're going to have to add up all of the components as reactants for all of these three steps, and all of the products for all of the three steps, and then remove anything that's on both sides, so is both a reactant and a product, and then you'll end up with the overall balanced equation. Now, if you do that correctly, this is what you will get. You'll get that the C4H9Br plus 2 water molecules goes to form C4H9OH, so that alcohol there, plus Br minus ion, so a bromide ion, and H3O plus. Okay. That means that you can see that in the reaction mechanism, we also have some intermediate steps, and we have some intermediate products. So which of these species is an intermediate? So that will be something that is a product of one step and then a reactant of one of the later steps. So that means it's created in one step and then used in a later step. So an example of that is C4H9 plus. And the other example that's a product of step 2 and then is used in step 3 is C4H9OH2+. So how do we link kinetics with reaction mechanisms? Well, what we do is we determine the rate law of a reaction by using experiments. And then we devise what we have as an idea of what the mechanism might be, so the number of steps involved in that reaction, based on a knowledge of the rate law and also a knowledge of the overall balanced equation. Then we can predict the rate law from that mechanism. If it agrees, then we look for additional supporting evidence, and we think we're on the right lines for what the reaction mechanism should be. And if it doesn't agree, we rethink the mechanism that we have. And so we can link the two. What you need to remember is you cannot tell the reaction rate order from the overall balanced equation. Okay, we've said that, I think, in every lecture now, so it's really important to remember that. The molecularity of each elementary step determines the rate order of that step. So elementary steps, then the rate of those steps can be determined by their own rate order or rate law, because they are an elementary step. Not all steps matter for the overall reaction, only the rate limiting step. All other steps within your reaction occur faster than that step, and so don't limit the rate of the overall reaction. And the final thing to remember is the sum of all of the elementary reactions, so all of the steps in the reaction, has to equal the overall balanced equation of the reaction. Now, it'd be quite useful to visualize this process of a reaction with this diagram. So in this diagram, we have energy at one side against reaction coordinates. So that's the progress of the reaction along the bottom. So to start with, I'd like you to think about annotating this reaction profile with the positions of reactants, products, activation energies, transition states, and intermediates. So let's start by saying that this reaction path here is a two-step reaction. So it goes from the reactant, which we can call A, to an intermediate as step 1. And step 2 takes that intermediate to form the product. So where would you put A, I, and B on this reaction pathway? So you would put A and B at the beginning and the end of the reaction pathway. So that's your reactant is A and B is the product. And the intermediate will be the intermediate minima there. So you can see that there is an energy peak to form the intermediate, and then there is an energy peak, amount of energy required to form the product. So the transition state and the activation energies can also be added to this pathway. A transition state will be a state where, if you're going, say, from the reactants to the intermediate, the transition state is a halfway point where some bonds have started to break and other bonds have started to form, but they're halfway through. So you get to a point where they are at their highest energy state, and then they could fall in either direction. They could break apart back to reactants or completely form into intermediates. So the transition states are the highest energy points for the two reaction steps. Okay, and the activation energy is the amount of energy needed to get to that transition state. So let's put these in. So we've got our reactants, we can put our activation energies in, and we've got the intermediate state there as well. So you've got your transition state and your going towards your intermediate, so transition state 1, and that's an activation energy which is EA1 to get to that first intermediate state, and then there's an EA, an activation energy required to get from the intermediate to the highest energy state of the transition state 2 and down to the products. Now, in this case, which do you think would be the fastest step? So if you imagine that you're a car driving along a road, and there are quite a few cars, there'll be a part of the process, perhaps if you're going from a dual carriageway to a single carriageway, it's the single carriageway area that limits the rate that everybody goes. Okay, that'll be the slowest part of that journey. So if you look at this, which of these two steps going from A to I or I to B do you think will be the slowest step? Well, the slowest step, if we go through these processes again, we can add in our slowest step and our fast step, and the slow step will be from A to the intermediate, because that's when you have the highest activation energy. So the larger amount of energy is needed to overcome that activation energy to get to that first transition state and then fall to the first intermediate. So that's your slow step, which means that's the step that determines the rate of the overall reaction. As soon as intermediate is formed, the intermediate will be formed at a slower rate than it will be able to be used up, because the reaction going from intermediate to product requires a smaller activation energy, so less energy to overcome that energy maxima that you see there. And then the last question that we might get from here is, do you think that the overall reaction here is exothermic or endothermic? Well, the energy is going down, and we can assume then that we have an exothermic process in the way that this energy profile is being set up. So our delta H for reaction is negative, making it exothermic. So that was a whistle-stop tour of linking reaction mechanisms to reaction rates and rate laws. And what we've done there is we've found plausible mechanisms that can be predicted using kinetics. And we've seen that not all the steps in that reaction profile will contribute to the rate, only the slowest step, and that's the step that has the highest activation energy. And this concept of activation energy is really useful now, and it builds on to what we're going to talk about in our next lecture.